how gravity affects the path of light, how gravity changes the path of light. If light does not have a mass, then how gravity could change it? If gravity is a force, then how it can change the path of a photon? Does massless objects are drawn towards gravity? Well, I'm going to answer all these questions in this video and clear out all the misconceptions about mass, gravity, photon, how the path changes and everything. We are also going to look into some of the preconceived notions that we have for concepts in physics and understand the right thing in the right manner. My name is Shaunak and you're watching this video on my channel Physics for Students. Let us understand this question, how gravity affects the path of light. Well, as usual, first we would look into the topics that we are covering today. So first we will understand what are photons. Then we will understand whether gravity is at all a force. Then we will look into the curvature of space-time and go deep into special and general theory of relativity. We need to look into some of the important postulates of general relativity, how we can measure the curvature, how photons moves along a curved path, and what is the deflection of light due to the presence of mass. And finally, we will look into a bigger picture, which is a kind of a surprise that you need to wait till the end of the video. So we are going to take one by one all those topics and clear some of the misconceptions of physics and understand what is right. So first, let us start with understanding what is a photon. Well, before understanding what are the photons, I would like to go back a little bit in the history of the origin of the word. So the photon is an elementary particle that is quantum of the electromagnetic field, including electromagnetic radiation such as light and radio waves and the force carrier for the electromagnetic force. So photons, as you see here, it is a wiggling wave, is a massless, so they move close to the speed of light in vacuum. The photons belongs to the class of bosons. So as with the elementary particle, photons best explained by quantum mechanics also exhibits what is called a wave-particle duality, their behavior featuring properties of both waves and particles. Okay, so Arthur Compton used photon in 1928, right, referring to this letter of Gilbert Newton Levy, who coined the term in Nature in a letter to Nature on 18 December 1926. In most of the theories to the 18th century, light was pictured as being made up of particles. Since particle models can easily account for their refraction, diffraction, etc., wave theories of light were first proposed by René Descartes in 1637, Robert Hooke in 1665, and Christian Huygens in 1678. However, particle models remain dominant chiefly due to the influence of this person, Sir Isaac Newton. In the early 19th century, Thomas Young and August Fresnel clear demonstration of the interference and diffraction of light. Later, James Clerk Maxwell's 1865 prediction that light is an electromagnetic wave confirmed experimentally in 1888 by Heinrich Hertz's detection of radio waves. This seemed to be the final blow to the particle model of light. As shown by Albert Einstein, some form of energy quantization must be assumed to account the thermal equilibrium. So this actually shows a little bit about the origin and the history of the word photon. Okay, so we know that photons are massless because they travel close to the speed of light, and it includes all these radio waves, microwaves, it includes infrared, visible light and everything. Now there might be a question in your mind that photons have no mass, but how can they have momentum? I have exactly addressed in details about this question. Here is the snapshot of my video. You can go into my playlist and check out something very interesting related to the subject, that photons, yet they have no mass, but how can they have momentum? So we can presumably slow down light in optically denser medium, but in reality light travels at the speed of light, that is c. And what we can see is that a photon always has to travel at the speed of light because it has no rest mass. If you can the photon at rest, then since it has no rest mass, it has zero mass energy. So here is the photon at motion in the form of wave, and in the form of rest, this is just at rest. So now that we have understood photons and what is a photon comprises of, then now we need to understand that what is gravity, because until we understand what is gravity, we won't be able to understand how it affects the path of a light. Now the most important and intriguing question that comes into your mind is gravity a force? Now, with the advent of Sir Isaac Newton's famous Philosophiae Naturalis Principia Mathematica, he framed the laws of universal gravitation using this formula we know. And the second law of motion in modern terms can be written as this. This is the Newton's second law. And we can use this one. This is the momentum formula, and we can get this. And since we apply this to massless particles, that is a constant mass, we can take out this m and we can substitute dv by dt, that is the what is the formula of momentum, and then what we get is F equals to ma. Now what we need to understand that this is a kind of a simple pictorial derivation, you can say, of Newton's second law of motion. The question is that, as you can see this, these are all related to the moving of bodies, which are force, acceleration, momentum, etc. So the question is that, can we measure force in Einstein's general theory of relativity using the same old Newtonian concept? Also the question is that, what is momentum, force, acceleration in general relativity? And is the push or pull that we feel due to gravity, right? Is it the same in general relativity? Because until and unless we understand that whether it is a force, the same force which is used in general relativity, we won't be able to answer this question, does gravity or how gravity affects the path of light? Before that, we really want to understand, can we extend the old Newtonian concept into general relativity? If we can do so, then we can call it gravity. Otherwise, okay, what will we call it otherwise? Coming into the next part of the video. Okay, so we would look into something which we called a curvature, and that actually took place when Einstein generalized or extended Newton's classical laws into the theory of relativity. And when we are going into this special and theory of relativity, I would like to quote this famous equation, that worldly cloister where I hatched my most beautiful ideas. Now this is actually the time when we are talking when Einstein was a patent clerk, right, in the Swiss office in Bern, and it was all cloistered with a lot of noise, yet he hatched one of the most beautiful ideas. What are those ideas? Let us look at now. The day was 30th of June 1905, and the Annus Mirabilis papers are the 4 papers that Albert Einstein published in Allgemeine der Physik, or Annals of Physics, a scientific journal, in 1905. These 4 papers were major contributions to the modern physics. They revolutionized science's understanding. First was photoelectric effect, for which he won the Nobel Prize in Physics. Second was the Brownian motion, that is the temperature of a substance in proportional to the average kinetic energy. Third one is the theory of special relativity, and the fourth one was mass energy equivalence, which led to E equal to mc square, which led to the discovery and use of atomic energy. Now these 4 papers, together with the quantum mechanics and Einstein's later theory of general relativity, are actually the foundations of modern physics. Okay, so let us go forward and understand what actually special theory of relativity has proved us. So there are certain postulates of special relativity which is important in order to understand about gravity. It says that the laws of physics are invariant in all inertial frames of reference and the speed of light is constant. So here is a nice kind of a pictorial depiction. It shows that the Newton's law F equals to ma is still applicable in inertial frame of reference. So what we can deduce from here is that we are still in the realm of gravity. That means we can apply the use of F equals to ma in special theory of relativity, which deals with inertial frame of reference, and we can well certify that yes, this is gravity. However, the Galilean's transformation something looks like this, and it says that acceleration is the same in the both frames of reference. Now, as we know that Einstein later generalized the postulates of special relativity and the equations further into general theory of relativity, we call it special only because it is something very special and restricted only to the inertial frames of reference. So the special theory of relativity says the laws of physics are invariant in all inertial frames of reference, which led to unification of space-time into space-time as a whole, and the speed of light in vacuum is the same, which means both time and spatial distances are no longer absolute. This was the cornerstone of the special theory of relativity, which led to the identification of space-time, and spatial and distance are no longer absolute. However, the laws of physics remains the same. Later few years after thinking about the special theory of relativity, Einstein generalized into general theory of relativity. What was that thinking that led to this magnum opus general relativity? Let us look into this. So we see that there is a non-inertial frame of reference, that means one that undergoes acceleration. That means if it is undergoing an acceleration, there is nothing which is called a fictitious force, because Newton's law works well with everything except which are moving close to the speed of light. Then what are the limitations of special relativity? We can tell it is not a limitation but something which is extended to non-inertial frames of reference. So we call it no limitations, right? So this was the thought which turned to Einstein, that he thought that if a man falls freely, he could not feel his weight. This simple thought experiment led me to the theory of gravity. If you're standing on a floor and suddenly the floor moves off and you're falling freely in space, then that feeling and that you don't have a weight is similar to something which led to the theory of general relativity. So there is something which is called the principle of general covariance, which shows that the laws of physics should be independent of an observer's motion, and there is equivalence principles which says the gravitational acceleration is the same for all observers in a gravitational field. Remember that we started this part of the video trying to find out that what is curvature, and earlier we noticed that can we call gravity as a force, because we are now looking that whether we can apply the Newton's law in general theory of relativity. So here the principle of equivalence, that gravitational and inertial forces are similar to nature and they are indistinguishable, and the gravitational force as experienced locally while standing on a massive body is the same as observed by an observer in a non-inertial frame of reference. What do I mean by that? Simply, if you're standing on a floor, you experience a weight on your feet, and if an elevator is moving upwards, accelerating upwards, then you feel the same kind of a force. So what does that mean? That gravitational and inertial forces are the same. So here is a thought experiment, or Gedanken, which Einstein performed. And it actually showed that when you're shining a light and an elevator is moving upwards, then there is a bending of the light. So the light rays are no more straight and it bends. So let us look further into this. I would call it, this particular experiment as something similar which Einstein's Newton apple insight. That means when Newton was sitting at the garden and the apple fell on his head, he discovered gravity. Similar kind of a thing happened with Albert Einstein. So here you see that this is the photon emitter, and the elevator is accelerating upwards, and on the right hand side you see this is the apparent path of the photon. So the question is that what actually bends the space-time? There is nothing called gravity, and gravitation and inertial forces, if they are same, indistinguishable, then what actually changes the path of a photon? That is actually called a space-time curvature. So now we know that there is nothing which is called a gravity. The bending of the light is basically due to space-time curvature. But hold on, the question is that if this is a space-time curvature, then what actually causes the space-time curvature, or we can say that how can we measure curvature, coming up in this part of the video. So till now we have noticed that there is a curvature and there is nothing which is called gravity, because inertial frames and this is the same. So now we need to know that how we can measure curvature. So I would like to give you a simple example of Jupiter, Earth and Mercury. And because the mass of Jupiter is high, you can see the curvature as denoted in this dotted line in red is more. So the gravitational acceleration g is also more. Compared to that of Earth, the mass is lesser than Jupiter, so the curvature is less, so the weight and the g. Compared to that of Mercury, it is even lesser than Earth and Jupiter, so you see that this red line is not that dent, and we get the g and the I would say the weight of Mercury to be lesser. Now this is just a kind of an I would say a kind of a simple example to show you, but what actually led to the measurement, this is the famous Einstein's field equation, and this contains one Ricci curvature tensor, metric tensor and Riemann curvature tensor. Ricci curvature tensor actually measures how the matter changes from flat to curved space. Metric tensor is the causal structure of space-time, and Riemann curvature tensor measures the curvature on Riemann manifolds, and stress energy momentum tensor basically measures how matter moves through space-time. Don't worry, if you're really wondering about those difficult and complex terms, go to my playlist on general theory of relativity, where you will be able to find each and every term in detail. They have been explained along with the mathematical derivation. So let us ignore what we understood is that the measuring of the curvature is done by Einstein's field equation, and then now we can call this left hand side is basically the measuring of the space-time, right? What it measures is the geometry of space-time, and the right hand side actually measures the matter energy content of space-time, that is called the matter movement, and both of them are equated by an equal to sign. And we now know that space-time tells matter how to move and matter tells space-time how to curve. So this F equals to ma, now let us see, can we apply to general theory of relativity? What we see that this F equals to ma motion gets further into something which we call geodesic. We will look into the video, and the gravitational law gets extended to what is called curvature. From there we can say that so we cannot call this as a force. So one part is clear, that we cannot call gravity as a force. All we can say is that gravity is a curvature. Now that we have understood and we have laid the foundation that gravity is not a force but a curvature, so the question is that how do the photons travel along this curved path? That is what we are coming up in this part of the video, how photons moved along a curved path. Okay, so if you're familiar with this term, which is called geodesic, which means that the shortest distance between 2 points, this is the shortest distance in a triangle, this is also the shortest distance, and if I take out a curve, then if I get 2 points, what will happen, that the shortest distance will be a curvature. And in this particular manifold also, the shortest distance is basically the curvature. So if you take a tram, and if you really want to know in which path this tram will travel, then what we see is a curved path, or for example the tram line, and we can say that the tram will be traveling along this. So from here we infer that geodesics are simply the shortest path between 2 points. Further we can extend, as you can see, that this straight line notion is extended to curved space-time, and gravity is due to the curved space-time, and this presence of energy or matter actually causes the presence of this curvature. And here it is, an object moves through space-time in straight line, but if the space-time is curved, it will obviously move in the line following the curvature. So from here you can understand that if objects are moving in this curved path, then it will be the photon. But before that, we need to understand this one also, that this effect of curvature or the presence of mass is what we call gravity. Okay, so what we see here, often you will see this kind of a photograph or illustration when you are learning general relativity or relativity, this, and this, right? So I would like to tell you what actually this means. So here you see these small points are called differentiable manifold. That doesn't mean anything really heavy or something complex. It means that you can use calculus to differentiate it in order to do mathematics better. Here you see that if it is the sun and the earth, there is a kind of a dent, right? This is the curvature. And here you see these lines are a little bit dense, right? And here the lines are denser. And here the lines are a little bit loose. So if there are two people standing, one here and one here, so you can understand there's a certain curvature which are denser and certain curvature which is less denser, right? So from here what we get is that the lines are loose. So this is actually what happens when you're traveling along the geodesics. This blue line, this is called geodesic path, and this is known as the metric tensor. Don't worry, you can skip what is metric tensor, but once you see the picture or this illustration in future in your study, you can understand what it means. So the small points are where you can apply calculus. The masses of earth and sun is the curvature, and the line that follows is the geodesic path where the photon will travel, and somewhere the lines are dense, somewhere the lines are loose. So here you see the straight path where the ball is moving straight. Forget about sectional curvature. So the size of the ball remains the same. This is important. Now if I take a kind of a path which joins at a point, that means it converges, you will see the ball size will shrink, right? And if I take a kind of a divergence like this where the geodesic path is this, then you will see the ball size is increasing. That means the size of the ball increases. Okay, so now that we have understood that this is the path in which objects move, and it actually moves along the curvature, and curvature is gravity, the questions still rises that what would be the deflection of the light, or how would the light will be deflected in the presence of mass, coming up in this part of the video. So now we are going to look into what is actually the deflection of light due to presence of mass. So if there are two particles or two bodies, then we can shine a light from one point to other. So it will basically travel in a straight line. Why? Because there is no mass. If I put sun around here, which has got a huge mass, and this blue dotted lines is actually the curved path, here you see how the photon moves. Right? So this is the answer to this basic question, that the photon takes the path of a geodesic that appears to be curved, and the curvature, why it happens, it is due to the presence of mass, right? And so here we can say that gravity is the bending of space-time due to matter. So I hope that now the conception is clear that gravity really doesn't cause the light to move in a different path. First of all, there is nothing called gravity. It is a space-time curvature. So if the curvature is there, just like the tram will move in that path, the same will happen. The photon will take the different path instead of a straight line. It will take the deflection wherever the curvature is. This has been proved in 1919, and we will come to that. So we can say that photons travel along geodesics. Geodesics can be thought as the shortest path between 2 points. In general relativity, the shortest path between 2 points might always be a straight line. And sometimes the shortest distance of a photon can be taken as 2 points, may actually be a curved path or a straight line, in which case it would appear us that gravity has an effect on the photon's path. The last line is important. Sometimes the shortest distance between 2 points may actually be a curved path, but in which case it would appear that actually gravity is causing the effect on the photon's path, but that is an illusion. It is just taking the curved path or the geodesics. So with Sir Frank Watson Dyson and Sir Arthur Eddington on 29th of May 1919, they conducted the famous, which is called the Eddington experiment, where is the earth and the sun, and the light beam shines over here. This is actually the location of the star, but it actually deflects, and this is the apparent location due to the presence of sun. So when the solar eclipse actually happened, what happened is that because of the sun's presence, the location of the star actually appeared somewhere else, and this is the angle of incidence, which is called the Einstein angle. And this actually proved Einstein's theory of relativity, that yes, due to the presence of mass, there is a space-time curvature. Here you can see that delta is basically the deflection, and this deflection is for a very small angle. So again, to repeat, this answers the question, the very beginning, that how gravity affects the path. First of all, there is nothing called gravity. It is just the space-time curvature, and the light or the photon just simply takes the path of the geodesics. So here it is the 1919 solar eclipse, and this is the news cutting where it shows Einstein theory triumphs. Although it was carried out earlier by George von Soldner, but it was later Einstein who proved it, and this bending of the light around massive objects is called gravitational lensing. And now we have studying gravitational lensing to try to understand dark matter and other areas of universe. So Arthur Eddington was truly very happy, and he wrote this poem, kind of a parody of Omar Khayyam's Rubaiyat, that "O leave the wise our measure to collate, one thing is at least is certain, light has weight, one thing is certain and the rest debate, light rays when near the sun do not go straight." Why? Because of the presence of mass and curvature. Okay, so now that we have understood the entire process, that curvature and the deflection of light, I would like to give you a bigger picture. I mean to say the bigger picture in the sense, where actually do we stand and what are the further scopes of research in general relativity. So you see, the geometric theory was developed by gravitation by Einstein and others, published in 1915. It generalizes special theory and refines Newtonian mechanics. So this inverse square law is further extended to the curvature of space-time, which you can see is further extended to sun, neutron star and black hole, which has got further intense curvatures. So the straight lines are now being understood as geodesics, and the time and space is now united in a lump, which is called space-time. And Einstein's general theory of relativity, or Einstein field equation, actually shows the presence of mass, that is the stress energy momentum tensor over here. And what we see, that there are other scopes like cosmology, black holes, gravitational time dilation and gravitational waves, which are further being studied as a result of this publication of general theory of relativity. So I hope you got the answer to the question. Quite a clean one, but I have to go through certain areas of physics and mathematics to make you understand. And I would like to thank you very much for watching this video. You can subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. You can contact me for anything at this email ID. You can look into my another YouTube channel dedicated to general theory of relativity, and you can follow me further if you want on my Facebook, Instagram and LinkedIn pages. Thank you very much for watching this video. Please put up your comments so that I can understand how do you react to this video. And Physics for Students will continue making videos, interesting subjects, interesting topics, and I will be back very soon. Till then, goodbye.